All right, so the streaming is on with audio on, so we are ready to go. All right, so the first thing is I'm going to go over the ungraded assignment. And Nick pointed out a mistake that I made that would make it, certain things, would be impossible without that fix. But that's fine, okay, because, you kind of have to think about it also. So we'll go ahead and talk about this first. This was your ungraded assignment because I wanted you guys to have something to work on over the weekend. So I'll give you some constraints. This is the part that I changed. It was the opposite way. Now it is saying y is a superset of 0 to as a set. Okay, because without that, it's impossible to do. Okay, certain ones would not be possible. Certain ones would be possible. So if you did work on the original version and you encounter problems, that's normal because the question was not formulated correctly to make it workable. So that's good too, because if you encounter the problem, that means you have understood those concepts correctly. Yes? Hmm? Well, let's work through these and then we'll figure it out. It cannot be injective anymore, and if it cannot be injective, it cannot be bijective either. So it's the injectiveness that is not possible. All right, so we'll go ahead and just work on this one, and I'm going to use mousepad or notepad because that's relatively easy to do. Okay, there we go. Okay, so we know X is just, the set of ABC. That is, you're not allowed to change this. We know Y needs to have at least 0, 2, but potentially something else, okay? So, that is up to you because you need that. And now we have to look at F, okay? So we want it to be neither injective nor surjective, okay? So this is the first one we want to work with. Okay, so how do we make it not injective and not surjective?
Can you move the window a little bit to the left?
Oh, because you can't see it, right? Okay. There we go. All right. Is it okay? Just a little bit more? Okay. I think I got everything else from the question, so we can just pull this all the way over. All right. So if we map every single thing in X to one thing in Y, and even if Y is the way it is, which is just 0, 2, we'll make it neither injective nor surjective. Okay, so I'll give you an example first, and then we'll talk about it. So we map A to 0, B to 0, C to 0. That is not injective because injection means every element in the domain needs to map to a unique element in the codomain. Well, this is kind of the extreme case of not being injective because everything mapped to the same thing in the codomain. It is certainly not injective. It is also not surjective, and to talk about surjectiveness, I'll just lock down Y to be just 0, 2, and you can see that there are two elements in Y in the codomain, but everything in X, everything in the domain only maps to one of the two elements in the codomain, and you can see how element 2 in Y is never mapped to. So that makes it not surjective. So this example is neither injective nor surjective. Do we have any questions about the first question, the first example? Are we good? Okay. Let's work with the second one. The second one wants to be injective but not surjective. Okay. So we'll write it down first. F is injective but not surjective. Okay, so for this one, Y cannot be just 0, 2 because you cannot have injectiveness when the codomain has fewer elements compared to the domain. So we need to make it at least 3, but in order for this not to be surjective, we need a little more. Okay, so we'll have 3 and 4 here. So now we can have F, being a set of two tuples. A goes to 0, B goes to 1, C goes to 2. Oops, there's no 1. So here's 2, here's 3, and that's it. So in this is not the only way to arrange things, okay? But the whole idea is you have to leave one element of y out and it is not mapped to. So in this case, it is injective because you can see how each element of x or the domain is mapped to a different element or unique element in y. But you can also see why it is not surjective because 4 as an element of the codomain, nobody maps to it. So are we doing okay so far? Every time you have a codomain that has more elements compared to the domain, it is automatically not surjective. Yes?
So even though question 12, for example, says that 02
Mm-hmm.
is a subset of y, in order for that to be true, wouldn't y have to stick to 2 elements? Or like it can also break it and just say that you can also make it a proper subset.
It only says it has to be a subset, doesn't mean that it cannot be a proper subset.
Okay, yeah, that's what I was asking.
Yeah. All right, so we got 2 done. Let's look at the third one. I think the third one is not injective, but it is surjective. Okay, so with that one, y can be just 0, 2, okay, without adding any additional elements. Because in this case, f can be mapping a to 0, b to 0, and then c to, we don't want it to be injective. Okay, that's not injective, but it is surjective. It is not injective because there are 2 elements of the domain mapping to the same element in the codomain. So now it is not injective. But it is surjective because in this case I define y to be just 0 and 2, and both elements are mapped to from elements in the domain. So this time it is not injective, but it is surjective. The last one says f is injective and surjective, which we also know as bijective because it has to be both in order to be bijective. So this time y has to contain exactly the same number of elements as x. So we just say 0, 1, 2, and then f has to map. Okay, this is one example. There are a few other examples for the mapping, but this is one way to do it. Because this time it is injective, meaning that everything in x is mapped to a unique item in y, and then it is also surjective because everything in the codomain are used up. They're all mapped to. Do we have any questions about the answer to the ungraded assignment after the correction? Because before the correction, it would not be possible to be injective. So are we okay? All right. Cool. Are there any other questions not related to the ungraded assignment about injection, surjection, or bijection? Or the concept of a function, not in the traditional sense that you get in your math classes, but in the sense of it is a set of 2 tuples where the first item comes from the domain and the second item comes from the codomain. So are there any questions about that portion? Okay. Are there any questions about aleph null, which is the cardinality of the set of all natural numbers? No questions about that? All right. So, without questions, we'll continue our discussion. Last time, yes?
I was walking through the parking lot and was listening to your live while walking, and I think your mic is too close because your audio is breaking out.
Oh, my mic is too close. Okay, let me check because I can check the mic here it's still in the yellow region.
It's dropping out, possibly.
It's chopping.
Yeah.
It's clipping. Well, I can change this thing actually has a gain that is let's go back here. Many years ago, I was using an MP3 player, and many of you are post MP3 player, in terms of when you were born. So you can ask your parents about it. So an MP3 player is a dedicated device, and the only thing it can do is to play MP3s. Okay, you can even set up playlists, on some of these things. The one that I had also has a mic, so I was using it to record lectures, and that was when I still wear like shirts with a pocket. So I would use that, to kind of put my MP3 player into it. The mic is so close to me that it was actually recording my heartbeat as well. So that was just kind of funny. Yep. Okay. So now we kind of go back to this one. We want to know whether there is a bijective function to map the set of all integers, which is kind of like the funny looking z, to the set of all natural numbers. Because if there is a bijective function like that, then we can call the cardinality of all integers to be the same as the cardinality of all natural numbers, which we also know as aleph null. Okay? So this is the way I define that function and utilizing ternary operator. So do we have any questions about this? Because we talked about this in the last class on Wednesday already. I'm hoping you guys do, for the most part, remember that. So are we good with this? Okay. So the question is, can we reverse this? Okay. And the answer is, yep, we can certainly reverse it. And the inverse function is like here. So what we do is we take a look at x mod 2 first. Because if x is an odd number, then this equality will be false, and then we'll use this method. If x mod 2 is in fact 0, then we'll use this. So this is how we map natural numbers back into the integer that maps to the natural number. So it's a two-way street. Okay, both of these functions are bijective. If you give me a natural number, I can find the integer that corresponds to the natural number. If you give me an integer, I know which natural number it maps to. Do we have any questions about the relationship between natural numbers and integers? So we good with that? The way you can visualize all of this is a natural. When you're thinking about integers, it's a number line that goes in both directions, right? And when you think about natural numbers, it has a lower bound, but then the other end is open-ended, so it's only going in one way, right? So you can kind of think about this map to be folding. So you're at the pivot point, which is 0, okay? And the way you do it is you fold the negative numbers or the negative values or the negative integers to the non-negative side. But in addition to the folding, you have to kind of space out things so that the non-negative integers will only map to even numbers, and that the negative integers will map to the odd numbers. So that's one way to kind of visualize the mapping process. So are we doing okay so far with that mapping? Okay. So now we talk about what is infinitely countable. It's a super short section. Basically, when you look at the cardinality of n, which is the set of all integers, it is infinite, but it is also countable. Okay, it's considered countable. So aleph null is basically saying something is infinitely countable. But we also have something that is infinitely but not countable. The set of all real numbers is not countable. Okay, so just minor differences, between what is. They're both infinite. Okay, both sets have an infinite number of elements. One is countable, and then the other one is not countable. In computer science, we typically work with things that are countable and not things that are uncountable. So are we still doing okay so far with the concepts? Okay. So now we want to see what else is countable. So this part, I think, unless you have already kind of worked this out on a piece of paper, it really helps to have a more graphical presentation. So I'm going to go for a graphical presentation for this part. using Zernal. And we'll go ahead and use a graph paper style. So there we go. All right. So the way we want to look at this is we want to look at a coordinate system. Okay, so this is your y, this is your x. I mean, this is nothing new. I mean, you guys know all this stuff already. So this is our 0, 0. And I'm just going to say this is 1, 2, 3, 4, 5, and so on. And then here's 1, 2, 3, 4, 5, and so on. So, just, when you look at the real screen, the way we count y is kind of opposite. In other words, the upper region of your screen actually has a lower number in terms of its y coordinate. Okay, but other than that, we know what this is. Okay, it's just a raster system. So if you want to number the cells, okay, we'll number this cell as 0, 0. This cell is 0, 1. This cell is 1, 0, 2, 0. Oops. Nope, I got it flipped. Yep, I got it flipped. Okay, so this is 1, 2, 1, 0, 0, 1, 0, 2. So we're just looking at squares, right? So we are looking at squares like that. So this is going to be 2, 0, and so on. So are we okay so far with the numbering of each quote unquote pixel in this two-dimensional space? Okay. So when you look at this space, and we'll just say that the x-axis goes indefinitely to the right-hand side, and then the y-axis will go indefinitely to on the vertical axis. It just keeps going up. So when you look at each axis, it's kind of like a natural number, right? Okay, so you have natural numbers going this way, and then you have natural numbers going this way. Is that okay? Are we doing okay so far? All right. So what about the set of all of these coordinates? Okay, so we'll look at the set of all the coordinates, and we'll just say it is C for coordinates. So C is pretty easy to define because it is the Cartesian product between natural numbers. Does that make sense to you? If I want to define a set so that every coordinate is in that set, in this two-dimensional space, that really is just the Cartesian product of natural numbers. Because the first item of a two-tuple has to be a natural number, starting with 0. The second number in the two-tuple inside C also has to be a natural number. So are we doing okay so far with this? Okay? So the next item I want to say is to say that, well, let's look at the cardinality of not the natural number, but the Cartesian product between natural numbers. So we're looking at the Cartesian product of C in this case, which is the Cartesian product of natural number and natural number. We want to look at the cardinality of this, okay? What if I were to say that this really is the same as the cardinality of natural numbers, which by definition is aleph null. So we have a little squiggly n and a null here. Would you buy this? Okay. Huh? But this looks kind of weird, right? No? But why are they the same size, right? Because it doesn't seem to make sense, okay? Intuitively, it takes a little bit of steps to make sense out of this. So the notes, also tells you how to look at this so that it makes sense, okay? So the way you do it is, we'll just start to number these squares. This is 0, this is 1, this is 2, 3, 4, 5, 6, 7, 8, 9, and so on. So we start to number the cells, or we number the squares diagonally, like this, and then when we encounter the end of that diagonal line, we go on to the next line, and then we go again. So we sweep from lower right-hand side to upper left-hand side for each diagonal line. And then we move on to the next diagonal line, the next one, and so on. So that seems like an interesting way to number each cell. Okay, so let's go ahead and check this out. Okay, so I'm gonna make a slightly better table here, and then we'll start to chop it up into cells. And then I'm going to use two different colors. We'll use blue. Does it look blue? Yep, it is blue. For the two-dimensional coordinate, starting with 0, 0. And then we have 0, 1, 0, 2, 0, 3. And this is 1, 0. This is 1, 1. This is 1, 2. Did I flip again? Yeah, I flipped it again. Sorry. Or you can just kind of do some conversion like that. I'm going to fix it. So, okay, this is 0, 1, 0, 2, 0, 3. And we'll just work out a few of these. Okay, this is 1, 1, 2, 1, 3, 1, 1, 2, 2, 2, 3, 2, 1, 3, 2, 3, 3, 3, and so on. So the blue stuff is really just the usual way that we name a square or a pixel in a two-dimensional space. I'm going to switch to a different color. Okay, let's say green, to give us the natural number. So the natural number of this corner, we start with a 0. Then we go 1, 2, 3, 4, 5, 6, 7, 8, 9. And the next one's going to be 10 over here. So are we getting a general idea of how to assign natural numbers to the squares? Okay? So, hey, that seems to be a bijective function, right? If you give me a two-dimensional coordinate where the x and the y are both natural numbers, I should be able to tell you what natural number it maps to, right? Are we good so far with that? Okay. And because of the way we seem to be sweeping the diagonal lines, it doesn't seem likely that we'll be mapping two different two-dimensional coordinates to the same natural number. We're not reusing natural numbers in these squares. So it seems like we got a at least injective function. But is it surjective? That's the other question. Are we going to skip certain natural numbers where no two-dimensional coordinate is going to map to? Doesn't seem like the case, right? Because we are continuous, it's contiguous. The way we assign natural numbers to a square is contiguous. We're not skipping anything. So in concept, this function is bijective. Okay? Even if you know how we are doing this, if I ask you, what is the natural number corresponding to, 27, 16, are you going to have a huge graph paper and actually fill it up to give me what natural number is going to correspond to the two-dimensional coordinate of 27, 16? I hope not, okay? Because, the whole idea of computer science is to do what? Automation and computation, right? So if we are going to use a large graph paper to figure this out, we're kind of defeating the whole purpose of computer science. Is that making any sense? Okay. So we want to derive a function where we can map a two-dimensional coordinate to a natural number using this particular way. Is that okay? Right? Okay, so let's switch back to the notes. Okay. And this is just an example, okay? It's equivalent to the picture that I have shown you, okay? It's just, listed in a way, that is linear. So the first question is, how do we come up with that equation? How do we come up with mathematical function, a closed form expression, so that I can compute the natural number. If you give me the two-dimensional coordinates x and y, I'll give you the natural number that is supposed to be in that cell. Okay, so what is the first observation? Okay, so when you're trying to derive expressions, when you're trying to derive a program, you're trying to generalize, okay, which is also called abstraction. You're trying to figure out a pattern, okay? What is the pattern? Yep, go ahead.
Along the rows,
Mm-hmm.
you can see that it goes 1, 2, 3, 4,
Mm-hmm.
and probably continues. And then you can see vertically it goes 2, 3, 4. And then also you can see in the second, like if you move one over vertically, you can see that the first difference is 3 and 4. So the difference goes up by 1 vertically and up by 1 when you go up.
Okay.
Horizontally.
So there's certainly a pattern to it, right? Now the pattern has everything to do with how we assign the numbers, okay? It has to do with the diagonal lines. So we want to look at the diagonal lines, right? So the first diagonal line only has one single pixel. The two diagonal line has 2 pixels. The next diagonal line has 3 pixels. The next diagonal line has 4 pixels, and so on, right? And it makes sense, right? Because where you start the diagonal line, that determines how many pixels you have to move horizontally. But every time you move it horizontally by 1 pixel, you're also moving it 1 pixel vertically. So it would take exactly the number of pixels horizontally in order to fill up that diagonal line. Is that making any sense? Okay, so let me just try to put this in a way where we can see it, okay? So we'll just go ahead and go to a particular pixel here, dot, 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 and this particular pixel has x0 as its coordinate, okay? We don't know exactly what x is, because the idea is to just give you a pixel, which is at the base of the entire thing, and we know what is the x coordinate. Do we know the number of pixels along that line? That's the question, okay? So what do you think? What do you think is the number of pixels along this diagonal line? So if I were to draw a diagonal line and fill the diagonal line with numbers, kind of like this, how many pixels are on that diagonal line? It's related to x, right? But it's not exactly x. It's x plus 1, okay? So we'll say there are, okay, x plus 1 pixels along this diagonal line. Okay, so every time we get an observation like this, we better double check and see if it is true already for things that we have already worked out by hand, okay? Very simple stuff. This is, in this particular case, x is 0. And how many pixels do we have with this diagonal line? 1, okay? Starting with this pixel, we got 2. Starting with this pixel, we got 3. 1, 2, 3, right? So that observation seems to be correct. Are we good so far? So once we know how many pixels are in a particular diagonal line, the next one is to try to figure out what is the natural number, okay? If I were to try to figure out the natural number that goes here, now I understand eventually we want to be able to figure out the natural number for all the pixels. But for now, we're just looking at the baseline, okay? We're looking at the pixels where the y coordinate is a 0. We'll start with that, okay? So what do you think? How do we work that out? Well, this is the first one. We start with 0. This one has to include all the pixels in all the previous diagonal lines, right? But since we only have one single pixel before, it starts with 1. So 0, 1, 2. This one has got 2 diagonal lines before that. The first diagonal line has 1 pixel, the second one has 2, so it's 1 plus 2, and that makes it 3. Is that okay? This one, okay, well, we keep adding. This is 1 here, 2, 3. So it's 1 plus 2 plus 3, which is 6. Are we doing okay so far with this generalization. Okay? So if we want to look at this particular value, we'll give it a name. We'll call this, I'll call this D, okay? The natural number that is corresponding to pixel x0, okay? So what do you think D is going to be? Well, it looks like we have to keep adding stuff, okay? It's going to be 1 plus 2 plus 3 plus 4 plus blah, 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 okay? But when do we stop? Do we stop at x? Do we stop at x minus 1? How do we find out when we stop? You can reason it out, right? That's one way to do it. But I'm lazy, okay? Sometimes I just want to observe it and then confirm it later on. So you just pick, say, okay, what if x is 3? Okay, if x is 3, how do I come up with a 6 over here? We got 1 plus 2 plus 3. Oh, so we have to include x in the summation itself. We do not sum up to x minus 1. We have to sum to x for the natural number that is corresponding to the location x0. Okay, so we say D is 1 plus 2 plus 3 all the way up to x. Are we good so far? Okay, so you can look at this as a sigma, where I is the indexing variable of the sigma of the loop. It goes from, you can go from 0, because 0 doesn't contribute anything to the sum. So you can start with 0, you can start with 1, and that's what we're looking at. Are we doing okay so far with this? Yes? Okay. You look at the sigma and go like, okay, now we have a systematic way to calculate D, which is the natural number corresponding to x0, the coordinate of x0. That's good, okay? It's systematic. But if you just want to do the sigma using a program, it involves a loop. And the duration or the number of iterations through the loop is proportional to x, okay? So it's not really the fastest thing to do. We want constant time things if it is possible, right? So now we look at this and go like, well, is there a closed form where I can just kind of lose the sigma and just use multiplication, division, and some basic arithmetic operator to get this done? Some of you have seen this already in other math classes and you already know the answer, okay? That's great. But what if you don't know the answer already? How do you look at the pattern and then derive the answer? Write it out. Very good. Okay. So we are going to use the next page, okay? Page new after, to write this out, okay? So we're going to say D is 1 plus 2 plus 3 plus 4 plus blah, 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 x minus 1 plus x. Okay. So look at this thing and go like, it looks like, we have some kind of a pattern here. If I add the first item to the last item, the second item to the second last item, the third item to the third last item, they all sum up to the same thing. Is that okay? There's a pattern to it, okay? So we just kind of regroup things a little bit and we say, it's the same thing as 1 plus x plus 2 plus x minus 1 plus 3 plus x minus 2 plus blah, blah, blah. So we are basically starting on both ends, and then we are trying to move to the center. But here we have a little bit of a problem, because x can be an even number, it can also be an odd number. So when they approach the center, sometimes you just end up using all the items, because you have an even number of things between 1 and x. So that's great. Other times you have one leftover item. Go like, well, this thing doesn't have a partner, so it is just kind of all by itself. So how do we deal with that? Okay, any suggestions? Okay, so we'll look at two examples. Okay, so we'll say, what if x is 5? Okay, When x is 5, then d is 1 plus 2 plus 3 plus 4 plus 5. There's an odd number of items, okay? So if I group things, then we have 1 plus 5 as one item, 2 plus 4 as one item, and then 3 has nobody to pair up with it. It is kind of by itself, hanging out, right? On the other hand, if x is 4, okay, then it's, everything is kind of square because we can group the first one with the last one, the second one with the second last one, and we use up all the items. We don't have something that's just kind of hanging over. Is that okay? So it looks like we have two cases. It looks like we need a ternary operator to see whether x is odd or not in order to determine, okay, which equation am I supposed to use? Okay. So I'm not going to re-derive the whole thing because it is actually in the notes. So in the notes, I did use the mod operator to see whether x is odd or not, okay? If x mod 2 does not equal to 0, it is odd. If it is not, it is even, okay? So now we can, okay, I included 0 into it, but that's okay. 0 doesn't really contribute to the sum. So let me just zoom out one level because then we can see the equations, okay? So when x is odd, I use this equation. When x is even, I use the other equation. So let me show both of those. Now this has to do with me including 0 into the whole thing, and you're not seeing the entire width of my browser. I'm going to change the display because of the resolution that I'm using. So I have to modify this a little bit. The recorder does record in the wide screen format. So the recorder is fine. You're just only looking at a smaller portion of what is being recorded. So don't worry about that part. There we go. It's much better. Okay. So let me scroll a little bit back the other direction so that we can see the condition. There we go. Now, because I'm including 0, okay, so that means from 0 to 5, everything is fine. From 0 to 6, we kind of have an item that is kind of left over on its own. Okay. How did I go from here to here? I just broke up a single sigma into two different sigmas, right? And how do those two sigmas relate to the single sigma? How does this relate to this? What is the trick that I use to break this up into here? Look at the indexes. Look at the indexes of each sigma after it is broken up. You can see that the first sigma takes care of the cases when I is 0 all the way and including x minus 1, the whole thing divided by 2, because we know x is odd in this case, so x minus 1 is even. Even number divided by 2 is also a whole number, which is okay, right? Are we good so far? And then the second sigma starts with what? The end of the first sigma plus 1. It's just continuation. Okay? So, and it goes all the way up to x. So we don't really have a problem with this broken up form would have the same result as the original sigma. Are we good so far? I'm just looking at a even number of things, and I say this is right in the middle. You guys go to the first sigma, and then you guys go to the second sigma. That's it. Are we good? What about the case when x is even? Now, if x is even, and I'm actually including 0 in the sum, then we have an odd number of items. And that is when we go like, okay, what about that item in the middle? The item in the middle is going to be on its own, not a part of any sigma. So that's why we have the x divided by 2 all the way out here. Are we good? And then the first sigma basically is saying, okay, the first half of the sigma minus the item in the middle, you go here. The second sigma is, okay, not including the one in the middle, but everything after that would go to the second sigma. And that's why you can see there's a gap in between. Because the first sigma goes all the way up to x divided by 2 minus 1. The second sigma starts with x divided by 2 plus 1. The one item which is right in the middle, which is x divided by 2, is out here. Are we good so far? So I just broke up a single sigma into multiple sigmas depending on whether x is even or odd. Are we good? So what about from this line to this line over here? What trick did I use to combine the two sigmas back into one? Okay, well, I kind of skipped one step, okay, but what do you think, what trick did I use to make that happen? Yep. Reindexing, exactly. So I look at the second sigma and go like, well, can I look at this a little bit differently? In other words, I just look at the index to start with x minus 0, okay, and then it goes all the way up to x minus 1 divided by 2, x minus this number here. So I just change the indexing, but I'm still covering the same items. Are we doing okay so far with this one? Okay, let me see if I can explain this one. Okay, I'm going to move this up so that we can see the original sigma, which is this one here, and then I'll show you what trick I used to change it so that I can combine the two sigmas. Okay, so the first one, I'm going to use a loop notation here because that's basically what it is. So the first one says I goes from x minus 1, the whole thing divided by 2 plus 1, and we want the loop to continue as long as I is less than or equal to x, and then for each iteration I'm adding I, and then what I'm summing, okay, is just I. So we say sum plus equal to I in the first one. Oh, here's Rodney, and Rodney has something to share with you guys. It's good stuff.
Hey, that's right. So on opportunity this Thursday here on campus, we have a 2-star general coming specifically to our campus to discuss the future of cybersecurity. It's going to be this Thursday in the community room from 10 to 11, and then he's going to discuss cybersecurities, what you need to know, jobs, everything for our students. So I was coming over here to just announce it and see if anyone was interested in coming. Professor has all the information, or if you need more information on it, I'm right next door in 404.
And you have the flyers right here,
Yes,
so you can
have the flyer.
you can just read it off. So it's on Thursday from 10 to 11 a.m. in the Student Center boardroom,
Yeah,
which is
it's-
kind of like the smaller room of the
Yeah,
of the whole
exactly.
bunch.
So I'll put it up. There's outside. So if you guys have any more questions, just email me, come by, let me know. You have any questions now? Yes, no, maybe, not coming, not interested, or hurry up and move on. Okay? So everyone later.
Okay. All right, so this is version 1. Okay, so this is version 1. We are doing something with the sum, and you can kind of assume that sum is initialized to 0 to begin with. Okay, so now I want to look at a second version. Okay, version 2, and sum is also starting with 0, but I want I to go from 0 to x minus 1, the whole thing divided by 2, and I want I to be I want the loop to continue as long as I is less than, okay, actually, that's the initialization, and I want I to stay as long as it is less than or equal to x minus 1, the whole thing divided by 2, plus I. So now the question is, how do I change the term that I'm summing in order for the two loops to come up with exactly the same sum without changing x. So x is given already, but I want the two loops to do exactly the same thing. Okay? Are we doing okay so far with what I'm trying to do? I'm trying to take the second sigma and roll it into the first one. Okay? So you look at the first loop, okay? So you look at this loop here, and then you ask, what are the values of I? The first value of I is going to be x minus 1, the whole thing divided by 2 plus 1. The second value of I, okay, this is going to get very boring. Okay, that's plus 1. And then it's the same thing, except it's plus 2, right? So nothing very exciting here. And then the last value of the iteration, the last one that's going to be added to sum, is when I equals to x. Because the condition to stay in the loop is when I is less than or equal to x. So when I equals x, we have that one last iteration to perform, which is adding x to the sum. Are we good so far? Okay. So we look at the second loop, and we go like, well, we want I to basically cover the same range of values, except I itself, excuse me, we don't want I to go from this to stay with those values, but the item or the value that we're adding to sum, we want the same thing added to sum, just in different orders. Okay. So now we look at this and go like, how can we accomplish that? This is a plus 2, by the way. And then the second last item is when I equals to x minus 1, and so on. Okay, so there's a whole bunch of stuff in between here. Okay, so we look at this, and we know in the first iteration, I is 0. But the sum that we want to add, or the value we want to add to sum, is not 0. Okay, we want to start with one or the other end of the original values. And we look at this and go like, well, how should I do this? I want to have x included, as one of the values to add to sum, right? But I itself is starting with 0. So what if I were to say, sum is going to be added to using x minus I? Would that work? Because when I equals to 0, what is x minus I? That's just x, right? Is x one of the values that we added to sum in the first loop? Yes, it was the last value that we added, but the ordering does not matter because summation or addition is commutative. So the ordering does not really matter. Is that okay so far? Okay. So this is just x. What happens when I equals to 1? Okay, the value we'll be adding to sum is x minus 1. Okay. Oh, that is cool. That handles the second last value in the first loop. So now the question is, what do I need to do when I is x minus 1, the whole thing divided by 2? What would I be adding to sum in this case? It will be x minus I, right? And I is x minus 1, the whole thing divided by 2. And would that be corresponding to this particular value? What do you think? You have to remember x is odd. X is an odd number. Okay. Now, if looking at variables and expressions is a little bit too much, sometimes that happens to me too, you plug in values. Okay. So now you look at this specific case and you say, okay, I can't look at the equation and just kind of relate to it. So you just force a particular value and say, okay, I want x just to be a odd number. Okay, any odd number. So let's just say 27. Okay, so if x is 27, what is being added in this loop here? What is 27 minus 1? 27 minus 1 is 26. 26 divided by 2 is 13. 13 plus 1 is 14. Okay, so in the first iteration, 14 is added to sum. Over here, we want to look at this sub-expression here and ask, are we getting 14 here? That's the question, okay? Are we getting, are we adding 14 to sum? So you look at this and you plug in the same value for x. X is what again? 27. So we are looking at 27 minus 27 minus 1, the whole thing divided by 2. Okay. So you look at this is 27 minus 26 divided by 2. And 27 minus 13, right? That is indeed 14. Okay. So we doing okay so far? I just have to plug in a value to see. Okay, we can pull that up a little bit. Are we doing okay so far? Or not? Okay. So the trick is, if you look at something and it's too abstract because there are too many variables or there's an expression, plug in a specific value so that you can have a more concrete sense of whether the equation is working or not. Okay? But what is the big idea? The big idea is I can now just say that what am I going to add to the sum in each iteration? The first iteration has x minus I. The second iteration has x minus I. The last iteration has x minus I as well. So for each iteration, we just want to add x minus I to the sum. So now the two loops will do exactly the same thing. The first loop, which has the index going from x minus 1, the whole thing divided by 2 plus 1, going to x. The second loop having the loop index going from 0 to x minus 1, the whole thing divided by 2. By changing the expression I'm adding to sum, I can now make the two loops do exactly the same thing. Are we doing okay so far with at least the general idea of what I'm trying to do? A little bit? It's okay? All right? So getting back to the notes. So you can kind of imagine that I skipped one line here. So in between these two lines, we have this sigma changed so that we have the index is going from 0 to x minus 1 divided by 2, just like the first sigma. But the expression I is becoming x minus I. Are we doing okay so far with that intermediate sigma that is not actually in the notes? Yes? Kind of? Okay? So what we end up with, okay, let me see if I can do it here. Okay, so what we end up with is two sigmas. One sigma says I goes from 0 to x divided by 2 x minus 1 divided by 2. Okay. And the value that we are summing is I. The second sigma also has I going from 0 to x minus 1, the whole thing divided by 2. But what we are summing is x minus I. Is that okay? This is the step that is missing in between those two lines. Okay? So you look at these two and you go like, okay, we can set up one loop for the first sigma. I goes from 0 to x minus 1, the whole thing divided by 2. And then for each iteration, we add I to the sum. Okay? We set up a separate loop, a second loop after the first one, where I goes from 0 to x minus 1 divided by 2 again. Except this time, whatever we are adding to the sum is x minus I. Then you go like, that's not very efficient, because the two loops have exactly the same starting point, and they also end at exactly the same point. Why go through two loops instead of combining both loops into one single loop, and then we just say for every iteration, we'll be adding I and x minus I to the sum. Is that okay? That is what we saw in the class note. Okay, by combining these two, by re-indexing stuff, now we have this. So if you are semi-good with algebra, you look at I plus, in parentheses, x minus I, you immediately know, oh, we can simplify that. I doesn't serve any role in this entire thing. So that becomes just x, right? Because I is canceling itself. We just have x here. You look at that expression and go like, but x does not depend on I. X is a constant. X is already given to you. It does not depend on I. So if you are summing x exactly x minus 1 divided by 2 plus 1 times, why don't you just multiply? Is that okay? Is everybody doing okay so far going from the sigma to the multiplication? Because I'm just adding x a certain number of times. How many times am I adding x to itself? X minus 1 divided by 2 plus 1. Okay? Why do we have that plus 1? Because the index starts with 0. So we have that plus 1. Are we doing okay so far with that? Okay? So what about the right-hand side? Okay, so with this side, I'm gonna stay here. Well, let's take it one more step, 2 more steps. We'll finish the left-hand side first. So we went from the sigma to the multiplication, and then from here to here, what trick did I use? Okay, you guys are supposed to know enough about algebra to get to this class. Exactly. So this 1 is seen as 2 divided by 2. Now that we have a common denominator, we can combine or put the numerators into the same addition. So now we can look at x minus 1, the whole thing plus 2. Well, why don't we just say it is x plus 1, right? This side, this portion is just x plus 1, right? So if that is x plus 1 and we just have an x here, let's combine those two, and now we have a closed form when x is odd. Are we good so far? What about when x is even? Okay, so we do basically the same trick. So we look at this, and we look at these two sigmas, and we apply the same trick as before, so that we end up with only one sigma. Okay, x divided by 2 is still outside of the sigma. Okay, and then we combine the whole thing. From here, we can jump to here. Because you can see how we have I plus x minus 1, I plus in parentheses x minus I. So I get canceled out, and we are really just multiplying x to itself, x divided by 2 minus 1 times. But since we have a 0, so you have to add 1 to it. So we are just multiplying x by x divided by 2. Yes, go ahead.
The topmost sigma form, you said the x divided by 2 is not a part of that rightmost?
That is correct. So you can kind of imagine you have parentheses here, parentheses here. This is outside of the sigmas. Is that okay? So I use the same trick. Okay, I'm just re-indexing things. I'm changing the index to match the indexing of the first one, and then I have to adjust the expression that I'm summing in order to come up with exactly the same sum. So it's the same trick that I applied to the right-hand side. But of all the derivations down, what do we eventually find out? We found that it doesn't even matter. Okay, whether x is odd or even, we still end up with x times x plus 1 divided by 2. That's comforting. Okay, it's comforting that x can be 5, we use the same equation. X can be 6, we still use the same equation. So this is kind of showing you, how to kind of prove something, how to derive a closed form expression, which is x times x plus 1 divided by 2, when we started off with a sigma notation, which normally means, okay, you got to have a loop, sum things over, a certain range of indexes. Yes?
Because I'm curious, when you're doing a big process like this,
Uh-huh.
for the proof, because this is a well-known formula, I imagine you had a goal in mind when you were writing this proof, so it's like you knew not to stop. But like when doing something like this, if you don't know that they're going to be the same, how would you know kind of when to stop? How you feel comfortable with it?
Well, the objective is I want to have a closed form notation. So when I get to a closed form notation, I go like, okay, we can stop.
The sigma's gone.
Yeah. Yeah, once you do not need a loop anymore to perform the same operation. So this one, yes. So you're absolutely right. This is kind of well known. If you just look up on the internet, 1 + 2 plus dot dot dot, to n, if you, I'm guessing if you put it into Google search, it would find the right solution already. So with this one, it's really just working out the stuff in between that, kind of takes a little bit of time. Because intuitively it makes sense, right? Because you just group the first one with the last one, second one with the second last one, and the number of times you have to add kind of depends on 1/2 of where you're summing up to, right? So intuitively it makes sense. But why does it work with both even numbers and odd numbers? Okay, that's the other thing. So I cannot just take something as is. Okay, when someone says, okay, the sum of blah 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 is this, I go looking like, well, I can spot check it with a few numbers, seems to make sense, but I have to go through my own proof process to convince myself that, yep, I now understand why that is the case. So you don't have to do it in this class. This class is kind of, I show you the proof, just so that you can kind of see what goes through my mind when I encounter something like this. Now, is this the best proof there is? Probably not. Okay, I would not be surprised if there are shorter and more elegant proofs of the same thing. But it doesn't mean this is wrong. It may be just like more of a scenic route. Okay, you still get to the same destination. It is just that may not be the shortest one. All right. So after all of this, what are we getting? Okay, we haven't really gone too far, by the way, because all we have done so far is to say, oh, okay, if we are talking about a pixel that is at the bottom of the entire graph, we know how to calculate that particular d. Because now we can go back to here, and then we can say, oh, okay, this d is really just x times x plus 1, the whole thing divided by 2. That is all we have accomplished up to this point. Doesn't seem like we have moved a whole lot, but we actually have. So what do we do now? We plug in the x and see if it works for all the known cases. Okay, just because the equation looks kind of nice and I spent a lot of time to figure out the equation doesn't mean it's right. Okay, so we got to do some spot checking. So we'll take this one here, okay, and spot check. This is when x equals to 1. So you plug in x equals to 1 to this equation. What do you get? You get 1 times 2, which is 2. The 2 divided by 2 is 1. Ah, that matches. Let's skip this one and go over here and see if it works, right? This is when x equals to 3. So when x equals to 3, 3 times 4 is 12. 12 divided by 2 is 6. Okay, that seems to work. So this is how you can kind of try to convince yourself that the generalized expression does work, but it only works for pixels at the bottom of the entire graph. Are we good so far? Okay. So now we say, oh, this is great. Okay, we have a way to find the natural number corresponding to all the bottom pixels. But the idea is I want to be able to find the natural number for all the pixels, not just the one at the bottom. So now how do we deal with something that is not at the bottom? In other words, what about these guys that are not at the bottom? What do we do with those things? So the way we think about this, or the way I think about it, is I give myself, an example, okay? So let's say we're trying to figure out, I don't know, 4, 5, okay? So this is pixel 4, 5, and I want to figure out the value for pixel 4, 5. We know things on the diagonal line are sequentially numbered, right? In other words, we always fill in numbers within a diagonal line, starting from the lower right, and then we work our way to the upper left, okay? So that means I need to find out which diagonal line 4, 5 belongs to. Does that make sense? As it turns out, when you look at the x and the y value of all the pixels of the same diagonal line, There's a pattern to it. So let's check out what that pattern is. Okay, so let's just pick one diagonal line. Let's pick the last one, 3, 0, 2, 1, 1, 2, and 0, 3. They're all on the same diagonal line. What do you notice about the x and the y components of each coordinate? They add up to the same value. Okay, you can see 3 plus 0, 2 plus 1, 1 plus 2, and 0 plus 3. They all add up to 3. And 3, by the way, is quote unquote the number of the diagonal line because you have 0, 1, 2, 3. Okay? Okay. So if I go back to this example, we know that if I extend this all the way down, what do you think is going to be the coordinate right at the x-axis? It's going to be 9, 0. Okay, very good. So 9, 0 is the first pixel of that particular diagonal line, and we know the number, the natural number corresponding to 9, 0, thanks to the equation that we just worked out earlier, right? So we know this pixel has a natural number of 9 times 10, the whole thing divided by 2, which is 45. Cool. Then what do we need to do to work ourselves up to 4, 5? Just sequentially, right? We just add 1 to each displacement of y. To each time we increase y by 1, we add 1 to the natural number. So how many steps do I need in order to get to 4, 5 from 9, 0? Exactly 5 steps, right? So that means the natural number corresponding to 4, 5 is really just 45 plus the number of steps I need to kind of walk up that staircase, and it's supposed to be 50. Is that okay? I think we got a general equation now. So if I want to look at g as a function, where you give it, x, y as a coordinate, and it wants to return the natural number corresponding to that particular coordinate, we know how to do it now. Because we know that x plus y times x plus y plus 1, the whole thing divided by 2, this will give us the natural number corresponding to the base of the diagonal line that xy belongs to. Are we good with that? Okay. But that's not the number, the natural number corresponding to the coordinate of xy, because it is only the base of that particular diagonal line. The number of steps I need to walk up to get to the pixel that I really want is exactly y. So I just have to add y to the natural number at the base of that diagonal line. Now we have the natural number corresponding to coordinate xy. We good so far? So once we have this g function, okay, so let's see how we can write this g. Okay, so g is a function, and it maps the domain of all the coordinates in a two-dimensional space to the set of just natural numbers. That is what g is going to do. Are we good? Okay. So if you want to, okay, you can using your own time, you can plug this in, okay, plug in the various x, y of the pixels that we have worked out by hand, and see if g is returning the same value as we have figured out by hand. Okay, I'm pretty sure they do. They match. Are we good so far? Yes. So working this g out is, it takes a little bit of generalization and a little bit of observation, takes a little bit of kind of derivation in math, but it's relatively, I wouldn't call it too hard. Okay, once you start to look at things, from the diagonal line perspective and summation and stuff like that, it's not too difficult to get to it. remember what we need in order to say two sets that both have an infinite number of elements to be equivalent in terms of cardinality is we need a bijective function, right? And we kind of intuitively know that G is bijective because we know kind of it is injective. In other words, no two pixels will share the same natural number, right? It kind of makes sense because every time we have assigned a number, we just move on to the next available consecutive natural number. So we kind of intuitively know that it is injective. Well, is it surjective? In other words, are we going to leave some natural number unused? No, because of the way we assign the values, the natural number counter just keeps going up, and every time we increment, it's only incremented by 1. So we kind of intuitively know that it is bijective. But if a function is bijective, it means it has an inverse. Okay? Now that is the fun part, okay? Because now that we know G is bijective, we know there's an inverse function. There's an inverse function G inverse that goes from a natural set of natural numbers back to two-dimensional coordinates. In other words, somebody can say, Tech, let's take 2020 as a natural number. What is the coordinate of the pixel that has a natural number of 2020? Somebody can ask me that question. Now, since it's a bijective function, we know G inverse exists. The question is, what does it look like? And how do we derive it? Okay? So obviously one way to do this is to write a program where it just keeps calculating until it finds the coordinate of the number that we have presented to the program. So we will just linearly search for the coordinate. So that makes that algorithm proportional to the value that is given to us. If somebody gives me a number that is like 30,610,000,000, okay, it's going to take that much longer compared to a like 1 to compute it. That doesn't seem reasonable to me. So now the question is, how do we find the inverse of G? G itself is not hard. The inverse of G is a little bit more involved. Okay? So I can tell you one thing is I cannot explain all of that in 5 minutes. But I can tell you what you can do to help so that we can speed up the explanation on Wednesday is to read the rest of this. Okay, so G inverse, the discussion of G inverse is starting from here. It starts with to find the inverse function. So what is presented over here is not something that I copied from somewhere else. Okay, it's not from Wikipedia. It's not from another professor's website. I actually did this myself. Okay, as an exercise. Okay, because I want to go through this whole thought process and go like, okay, so how do I derive this whole thing? So you can just kind of read along, okay, follow along the reasoning, and then just go like, yeah, this makes sense. This kind of makes sense. This kind of makes sense. But if you want to go one step further, you can kind of go through the exercise in your own mind, okay? You just go like, okay, this is an observation. How do I make use of this observation for the next step? So instead of reading, just kind of reading along, you spend some time and see if you can come up with, the next step on your own. Okay? If you cannot, don't worry, okay? I spent quite a bit of time to work this out too, okay? But I want to at least be able to present how I think in this class, okay, and not just the knowledge. I want to, instead of presenting just the knowledge, okay, which Wikipedia has a whole lot, right? I want to be able to show you guys how I think, how I generalize, what pattern do I observe, how do I make use of the patterns that I observe, so that, if you can absorb that, great. If not, it's not something that is easily taught. I just do not know how to teach that part. But I will try my best to present all of that stuff. So if you can absorb that, it's good. So are we doing okay so far? Okay. So this takes a little bit of thinking. Okay. This part is harder than the first part. Okay. So I'll kind of stop the lecture a little bit short today because it's really hard to kind of get started with this and then stop and then restart again. So it's just 5 minutes anyway. So I'll see you guys on Wednesday, and I'll see if I can give you guys an ungraded assignment just so they can kind of exercise on these topics.